Chapter 9. The Blayhat-Arimoto Algorithms. We first introduce a notion in information theory called the single-letter characterization. For a discrete memoryless channel Py given X, the capacity C equals the maximum of the mutual information between input X and output Y of a single use of the channel over all input distribution Rx gives the maximum asymptotically achievable rate for reliable communication as the block length n tends to infinity. This characterization of C in the form of an optimization problem is called a single-letter characterization because it involves only Py given X, the transition matrix of one use of the channel, but not the block length n. Similarly, the rates distortion function R of d for an IID information source x sub k, which is equal to the minimum of the mutual information between x and the random variable x hat over all transition matrices Qx hat given x such that the expected distortion between x and x hat is less than or equal to d, is a single-letter characterization because it involves only the distribution of the generic source random variable x, but not the block length n. When the alphabets are finite, the capacity C and the rates distortion function R of d are given as solutions of finite-dimensional optimization problems. However, these quantities cannot be expressed in closed forms except for very special cases. Even computing these quantities is not straightforward because the associated optimization problems are nonlinear. So we have to resort to numerical methods, and the Blayhat-Arimoto algorithms are iterative algorithms devised for this purpose. In this chapter, we will first discuss a general alternating optimization algorithm. Then we will specialize this algorithm to the Blayhat-Arimoto algorithms for computing the channel capacity C and the rate distortion function R of d. And then we will discuss the convergence of the alternating optimization algorithms. In section 9.1, we consider a general alternating optimization algorithm. Consider a function f of u1 and u2, where u1 and u2 are multidimensional real vectors, and take the supremum of f over all u1 in some set A1 and u2 in some set A2, where AI is a convex subset of the nth dimensional Euclidean space for I equals 1 and 2. F, a function from A1 times A2 to R, is bounded from above such that f is continuous and has continuous partial derivatives on A1 times A2. Also, for all fixed u2 in A2, there exists a unique u1 in A1, denoted by C1 of u2, that maximizes the value of f. That is, f of C1 u2 and u2 is equal to the maximum of f of u1 prime and u2 over all u1 prime in A1. Likewise, for all fixed u1 in A1, there exists a unique u2 in A2, denoted by C2 of u1, that maximizes the value of f. That is, f of u1 and C2 u1 is equal to the maximum of f of u1 and u2 prime over all u2 prime in A2. Let U be the pair u1, u2, and A be the Cartesian product of A1 and A2. Then the double supremum can be written as the sup of f of u over all u in A. In other words, the supremum of f is taken over a subset of r to the power n1 plus n2, which is equal to the Cartesian product of two convex subsets of r to the power n1 and r to the power n2. Denotes the value of this supremum by f star. We now describe an alternating optimization algorithm. Let u sub k be the pair u1 sub k and u2 sub k for k greater than or equal to 0, defined as follows. We start with some arbitrarily chosen vector u1 sub 0 in A1, and then let u2 sub 0 be C2 of u1 sub 0. That is, the u2 that maximizes f for u1 sub 0. For k greater than or equal to 1, u sub k is defined by the components u1 sub k and u2 sub k, where u1 sub k is equal to c1 of u2 sub k minus 1, that is, the unique u1 that maximizes f for u2 sub k minus 1, and u2 sub k is equal to c2 u1 sub k. That is, the unique u2 that maximizes f for u1 sub k. Denote f of u sub k by f sub k. Then evidently, f sub k is greater than or equal to f sub k minus 1. We now give a schematic illustration of the optimization algorithm. We start with f of u1 sub 0 and u2 sub 0, and this value is denoted by f sub 0. First, we update u1 sub 0 to u1 sub 1. Then we update u2 sub 0 to u2 sub 1. After two iterations, we have completed one cycle, and we have updated f sub 0 to f sub 1. Then we update u1 sub 1 to u1 sub 2, and then update u2 sub 1 to u2 sub 2. Then we have completed another cycle, and we have updated f sub 1 to f sub 2. Since the sequence f sub k is non-decreasing, it must converge because f is bounded from above. We will show that f sub k tends to f star if f is concave. Replacing f by minus f, the double supremum becomes the double infimum, infimum u1 in A1, infimum u2 in A2, f of u1, u2. The same alternating optimization algorithm can be applied to compute this infimum. In the next section, the alternating optimization algorithm will be specialized for computing the capacity C and the rate distortion function R of D. Here is a graphical illustration of the alternating optimization algorithm. The x direction represents the u1 direction, and the y direction represents the u2 direction, where both of them are multidimensional. The oval shapes here represents the contour lines of a mountain. Starting from some arbitrary point in the mountain, we try to climb to the top of the mountain by moving either east-west or north-south. First, we moved east-west and get to the highest possible point in that direction. Then we move north-south to get to the highest point in that direction. Move east-west, north-south, east-west, north-south, so on and so forth. And hopefully, we will approach the highest point of the mountain. As we are going to show, as long as the mountain is concave, we will be able to approach the top of the mountain in this fashion.